Okay, everybody. Hello and good morning, and welcome to the second day of this Observatories Forum. Just going to start, I hope, with a couple of logistics announcements as soon as I can get this moving. Come on. There we go. Okay, just a reminder of the code of conduct. We're following the AAS Code of Ethics. If you haven't read it, the link is on the screen. In short, it simply says we encourage the free exchange of ideas in a way that is respectful at all times. So if you have any concerns on that score, I'm the person to reach out to. Day two, the agenda, we start with a session discussing radio and submillimeter. The unconference session will actually be in the second slot today. So feel free to jump on the Slack and post your ideas for what you'd like to work on during the unconference time. And then in the afternoon, we will return to both ground-based and space-based observatories. So just a reminder where to post your ideas for the unconference session. There is a tab under the Obs Forum 2025 Slack channel, and you can fill in the table or vote for a session that's already been proposed. And last, just a reminder that we have a planetarium show just for us here tonight. The planetarium is about 20 feet down the road, so it's not far to go, but it should be a really good show. So I hope you'll stay and join us for that. And that's all I had. So with that, I will hand over to our first speaker. And that is Nayana. And let me bring up your talk. That's not it. Okay, and if I hit play, voila. So I will give this to you and tell us all about time domain in the radio. Thank you.
Hello everyone, I'm Nayana. I'm a postdoc at UC Berkeley, working in the extragalactic transient group with RAF. So today I will talk about the need for multi-wavelength coordinated observations to understand various astrophysical transients. So this is the outline of my talk. I will start with the phase space of explosive transients and talk about the bigger questions in the field that as a community we are trying to address. Then I will move on to the multi-wavelength observations and what each band would tell us in understanding these events. Then I will highlight the entire workflow with a recent work or an extensive multi-wavelength campaign that we did in our group and what we learned about the physics of the system. And I will summarize and talk a little bit about what can be done to improve coordinated follow-ups in the future. So as I have shown here, the landscape of explosive transients is very diverse. We have the most common core collapse supernovae, thermonuclear supernovae. At the low energy end, we have galactic novae. There are tidal disruption events, much energetic jetted transients like GRBs. Now, most recent high cadence optical surveys are also populating the phase space of explosive transients with more short timescale events, and one very interesting class is the fast blue optical transients, FBOTs. That's one of my favorite objects. Now, as you can see, the way to address the question about progenitors and energetics is really a multi-wavelength game. I have picked my favorite band and showed the range in terms of timescales and luminosities here. So it basically tells you about the diversity in their intrinsic origin. Now, they also leave behind remnants, depending on the mass of the progenitor and explosion dynamics, either neutron stars or black holes, which are also fascinating objects to study physics in extreme conditions. Now, what is the bigger question which we are trying to address is what are the progenitors exploding to what type of transients and what they leave behind? And the key to answer this question is time-critical coordinated observations over the entire electromagnetic spectrum. Now, as I mentioned, the way each waveband probes, the physics each waveband probes in different types of transients would be slightly different because we are dealing with different physics and explosion mechanisms. So I will talk about what each waveband will probe with an emphasis on core collapse supernovae and F-bots in the rest of my talk. So the optical UV-IR emission from core collapse supernovae are mostly thermal radiation from expanding ejecta. If we catch them early enough, we can see the shock breakout signatures, then we see the photospheric peak. So once we probe the light curve, rise and peak luminosities, we get ejecta mass and energetics. If we carry out good spectroscopic observations, we can get ejecta compositions and velocities. Now, in the case of F-bots, this is not quite the story. In fast transients, the light curves rise, peak, and decay at very short time scales, like less than a few days. And the spectra remains blue, hot, and featureless for few weeks. Now, the high luminosity, they are like 10 power 44 Hz per second at peak luminosities, and the featurelessness in the spectra and fast timescales are in tension with traditional supernova models. Now, coming to the X-ray and radio side of the story, they basically probe the signatures of ejecta interaction with the surrounding medium. Now, whatever is the progenitor system, it has gone through some sort of mass loss, setting up an environment in the surrounding medium. Now, when an explosion happens, the bulk of the material is thrown to the surrounding medium at very fast velocities. Now, this creates a shock in the medium, and the interaction of the shock with the surrounding medium produces radio and X-ray emission. Now, the shock velocities are much higher than the velocity of stellar winds. And due to this interaction essentially probes a longer period of mass loss in the progenitor's life. So dedicated long-term follow-up observations is sort of the only way to track like thousands of years of progenitors' mass loss history. So they are very interesting in that respect. Now, this is not the only story of the X-ray emission. There can be copious X-ray emission from shock interaction, shock heats, plasma, and we see thermal X-ray radiation. There can also be inverse Compton component in X-ray emission. If there is enough optical photons, they can be upscattered to X-rays as IC scattering. X-rays can also manifest as central engine. One can see X-ray radiation from the center regions if it is a central source of accreting black hole or magnetar. Now, the signatures in spectral and temporal variation will tell us what is the physical origin of the X-ray emission, what we are dealing with. So the main physical parameters that we are deriving from X-ray spectral analysis or light curves are shock temperature, which basically maps to the shock velocity because the X-ray temperature is basically shock heated plasma. And there are complementary ways of finding the density of the surrounding medium. So one is from the emission measure and saying that I have this much X-ray luminosity, so how much plasma or the density will require to give me this much X-ray luminosity. Now also one can derive the density in the line of sight by looking at how much is the absorption this X-ray is going through. So these are different ways of finding densities from X-ray. Now, why coordinated observations are necessary? So for example, this is one example where, as I said, we can derive shock temperatures from X-ray observation.
Somehow.
Sorry?
Hello, to those folks online, if you could kindly mute while another speaker is presenting, thank you very much.
Thanks. So in the left panel, what I have shown is the X-ray spectrum that one can fit technically with only soft X-ray observations. As you notice, there is a degeneracy in the way we fit. It basically fit with different temperatures. But once we have the hard X-ray coverage with another telescope like a new star, we basically break the degeneracy, get accurate temperature estimates. Coming to the radio side of the story, radio is again shock, originates from shock interaction. Particles are accelerated to relativistic energies in amplified magnetic fields. Now, the radio emission will also be absorbed by different absorption processes like free absorption or synchrotron self-absorption. Now, as a result of competing emitting and absorption processes, what we observe is bell-shaped light curves or spectra, as I have shown here. Now, what is most interesting in terms of radio observations of astrophysical transients is in capturing the complete shape of the SED as I have shown in the panel. So the rising part or the optically thick side of the SED has a dependence on frequency as nu power 5/2 if it is synchrotron self-absorbed spectra, and it scales with the size of the emitting region and magnetic field as a power law. Now, the declining phase or the optically thin phase has a separate power law dependence. Now, at the peak where these two power laws intersect, one can essentially invert these equations and find R and B, which are interesting physical parameters. So as observers, what our goal is to catch both optically thick and thin side of radio SED and peak to constrain shock radius, magnetic field, and evolution of these parameters, which can be also used to infer CSM density and mass loss rate of the progenitor system. Again, why we need coordinated observation? This is an example from one of our recent study where, as you can see, the radio SED is spanning between multiple facilities. So we need GMRT, VLA, and NOEMA observations to map the complete evolution of the SED. So this is a supernova SED. This is the most famous 23 IXF, which was the nearest supernova of last decade. So in supernovae, we are not so pressed with time because radio usually appears like after a few weeks post-explosion, and if you manage to get different observations from different facilities within a week or few days, you can still recover the SED shape and physical parameters. But I will show you in a few slides how critical this becomes when you deal with fast transients like FBOT. Now, it's not just the end of the story. It's not enough to just coordinate soft and hard X-ray telescope alone or different radio telescopes alone. This is a SED of a transient covering radio to hard X-rays. As you can see, each waveband spectra are doing their own things, which says that we are dealing with emission coming from different components within the explosions environment. So far I have been trying to motivate and sort of link what different wavebands will probe and why coordinated observations are interesting. Now I will walk you through the workflow of one of that kind of transient, which we managed to get one of the best coverage in multiple wavebands. This is a very exciting transient because this is the brightest fast blue transient ever discovered. So a little bit more on FBOTs. As I mentioned, these show rapid timescales and very high luminosities. The peak luminosities exceeds 10 power 44 x per second. Now they are consistently blue for up to a month or so. Their spectra are extremely featureless, and all these observational characteristics cannot be explained in traditional supernova models. Now, even rare subclass of FBOT is LFBOTs, which are luminous end of this FBOT population, which show bright X-ray and radio emission. These are even rarer, and there are only 12 LF boards to date, which has got X-ray, radio, and UV optical observation. Now, alternate progenitor models include central engine-driven models like a magnetar or an accreting black hole at the center, or CSM interaction models, which says that the shock is interacting with a very thin, dense, confined CSM. So, 2024 WPP is the latest addition to the LF board population. It happened last year. It's at a distance of 411 megaparsec. That's not the nearest F board. For comparison, 2018 COW, which is the first LF board, which was only at a distance of 60 megaparsec. So we took this as a very exciting opportunity to follow this transient in great detail and to put some constraints and break degeneracies in progenitor models. So these are a few facilities that we use to follow this transient in real time. In the optical, we used LEAK, KEC, Gemini. We also used all existing photometry and data contributed by our collaborators. In the X-ray, we used SWIFT, Chandra, and XMM to cover the soft bands and NewStar to cover the hard X-ray bands. And in radio, we covered sub-gigahertz to millimeter bands using GMRT, Meerkat, ATCA, and ALMA. Now, let me walk you through the workflow starting from discovery alert to doing science with it. So basically, the transient alert came in on 26 September 2024, which was a Thursday evening. So what we do when a transient happens is first check all TO proposals which are approved. So as a team, we have around 50 approved TO programs at a time to follow different transients. So we check which all programs can be triggered on this event and submit DDT proposals for non-approved program. So we had, for instance, Swift Geo program approved for this event, which we went ahead and got all the XRT UVOT light curves. We had a couple of Swift Chandra XMM proposals, and for the remaining epochs, we submitted additional DDTs and coordinated the scheduling. So we had only one coordinated program, which was XMM NewStar program, and everything else were coordinated from our side. And we did the same for radio observations with all 4 telescopes. And our results are published as 2 companion papers last month. So let me get into a little bit more detail on the challenges on how we got on target and actually made these observations happen in a simultaneous manner. So for example, we had 3 programs approved for radio, but we didn't have coverage in the sub-millimeter bands. And F-boards are most exciting in the sub-millimeter bands. They are very, very bright. And what is the origin of sub-millimeter component is something which is which is open and not very well settled. So we first tried on a NOIMA DDT. So this target is not really a northern target. So we got back from the NOIMA DDT response saying that due to technical feasibility, we can't really approve your DDT request. You have to request ALMA or other telescope which you can use. So immediately we went ahead with the ALMA DDT program, which we heard back in less than 12 hours. And it got approved, and immediately the scheduling was approved. We could submit the scheduling block and get on target anytime. But we couldn't do it because we wanted to schedule it with all other 3 facilities. So that was the most exciting and fun part of the project, because all these 4 facilities are in 4 different continents in different local time zone. They have different way of scheduling and observing. For instance, ATCA is a radio observatory where they do not have a full-time operator at the site. Whoever is taking data is responsible to gear the telescope and get your own data. So how we did this is by keeping ALMA at top priority, especially because it's sub-millimeter observation. It's very sensitive to the weather condition in Chile. So we kept the ALMA as the prime scheduling body and kept a complete email loop communicating between ALMA scheduler with the scheduling team of all other 3 telescopes. So basically, once the Chilean sky was okay, the ALMA scheduling block was ready to execute, we immediately communicated with all other facilities and the operators in charge to get on target within few hours so that we get the SCD, which is near simultaneous. So, and this is what we obtained at roughly few weeks after the explosion happened. It's a very simple SCD with like 6 points, but this is one of my most favorite SCD of a transient. So that's pretty much the way we did the data collection. So I will show you a few results. So these are the optical UV NIR light curve coverage and the spectral sequence that we obtained starting from roughly a few days to over a month. And we sort of did the follow-up till the transient faded below the sensitivity limit of each facilities. Now, the right panel shows the derived physical parameters like the blackbody temperature, the blackbody radius, total UV optical IR bolometric luminosity, and the velocity estimates from this. Now, with this data set, there are multiple aspects and inferences that we present. So I will focus on one result which shows the strength of multi-wavelength observation to understand the big picture of the event. So this is optical to near NIR spectra of this transient. As you may notice on day 10, there is a clear excess. I'm talking about the blue curves, clear excess in the near infrared on top of the blackbody fit. Now, this is a classic feature seen in FBOT. So basically, this can be explained by free opacity effects in a medium just outside the optical photosphere. Now, from the luminosity and the spectral shape of this excess, one can put constraints on the density at that radii from the explosion center. So this is one result from the near IR analysis. I will loop back to this result again in a later slide. These are the X-ray light curves. This is doing a very interesting evolution, like very flat luminosity, then falling and a rebrightening. And you will also notice the spectral indices and the variation. It moves from a very soft X-ray spectra to a hard spectra, with the extreme hard spectra at the time of the flare peak. So this is not something we see very standard in core collapse supernovae or other explosive transient. So this is very classic of a situation where we are seeing X-rays diffusing out through an expanding ejecta, which has a varying optical depth to Compton scattering and photoelectric effects. Coming to the radio, I showed one SCD which we collected with all the facilities. We did that multiple times to see the SCD evolution. Now, there are many interesting features on this radio SCD, but one most striking feature is the evolution between days 17 and 32. You see an order of magnitude increase in the peak flux, which is not standard in core collapse supernovae or standard shock evolution in CSM. Now, we tried to understand different possible scenarios to explain this order of magnitude jump in radio SCDs. We tried off-axis models. It basically says that we are not seeing everything. Initially, there was a jet which was not in our line of sight, and it slowly came to our line of sight, and that's why we are seeing the increase. So it's an apparent effect. It could be. Or it's a real effect where at this time the shock is actually accelerating many more electrons and you are seeing an actual increase in radio synchrotron emission. Now, we could do several analytical tests to understand if which of these scenario are physically plausible. One example is that you know the overall energetics of the system. You say that this has a Lorentz factor of, let's say, 100, which we see in like long GRBs. And for a typical angle of 30-degree, how much this jet would spread out, and what is the time scale by which I will see the peak in such a system. So we know that we see the peak in 30 days, but for this energetics, such an off-axis scenario, we should have seen the light curve peaking in like 1 day. So that doesn't really go well with what we see. So basically, we tried these different approaches and converged that the shock is actually propagating through a dense medium. So this is an inference purely based on the radio SEDs that I have shown here. Now, how do we put things in perspective? These are all the density estimates that we obtained. The red shows the object which I'm talking about, and all the circles denote the other FBOTs in the sample. Now, the first point is where the SED evolution is like an order of magnitude. So we say that, well, at very short radii from the explosion center, the density is orders of magnitude higher than what we are seeing at much larger radii. Now, we also put the inferences from near infrared excess, the densities which was derived from free opacity arguments, which goes quite well with this picture of a dense medium surrounded in which the explosion is happening. Another interesting aspect of this result is that you might notice the strikingly similar density profile. All LF boards are falling in that short space where the density profile is 1 over r cube, and with very similar densities. It's not just the profile, it's also very similar densities that these observations are probing. So it certainly tells you something about the evolutionary track of the progenitor system. There is something global happening in a way that these densities are set up at similar scales, in similar profile, in all these systems so far known. So now what we have done, so I of course did not go through all the results which we have discussed in the paper, but what we have done is to put all these individual pieces of information together, coming from the optical light curve analysis, looking at all the spectral sequence, when the lines are forming, when the lines are not forming, what are the velocities we are seeing at what times, and how does X-ray behave. When does X-ray shows the rebrightening? When does the X-ray spectra hardens? Does it have any connection with when the lines are forming? How does radio behave? Why doesn't radio show up before that? Why does radio show that rise at a particular time? And put everything in perspective. So the final physical picture that we came up with is that the central engine is some sort of a accretion disk, which could be formed by the collapse of the merger-induced collapse by a neutron star. So we do not know what is the astrophysical setup that creates, but there has to be a central high-energy X-ray source and super Eddington accretion disk that drives fast outflows to the surrounding, which has to be at least 0.4 C, because we see shock velocities of that in radio. And there has to be a dense medium which is reprocessing this X-ray radiation and showing up in the optical. And the shock is breaking out from this dense medium, and we are seeing it at much later times. It's also very delightful to see that all the numbers also fall in place. If you see the radius or derived from radio analysis, and the radius that one derived from the black body optical photosphere, you always see the optical photosphere below the radio photosphere. So this is the picture which we have come up with, and I want to emphasize that this wouldn't have been possible if we do not have a campaign over the entire electromagnetic spectrum. I will summarize my talk. It's just one line. Coordinated pan-wavelength observations are very critical to map the intricate environment and explosion mechanisms of transients. These are a few thoughts on how we can improve these coordinated follow-ups in the future. A lot has been discussed on similar lines yesterday, but I will stop here and take any questions. Thank you.
Thank you very much. That was a really excellent summary of all of the physics involved for those of us, especially who don't work in the radio.
Thank you.
So we have time for one quick question.
I think that's one of the science questions. If somebody has a coordination related question, then I think I will just ask later.
Okay.
If you prefer. Yeah, but
I have one question about the observation campaign you did for WPP. When you were putting in the DDTs, I appreciate what you said about for the radio, you're under less time pressure than they are in the optical world of near infrared. But did you have to have the observation requests ready to go? Or is that something that you have to tailor to every single event?
It has to be tailored to every single event, but we do it the moment the transient appears in the alert. We do not wait even to confirm if it is the top priority transient. We get it ready anyways.
Okay, that makes sense. Okay, I'm not seeing any questions online, so let's thank Nayana again. Okay, and our next speaker is virtual, so let me escape out of that. Hello, Lukasz. I see you online. Lukasz Wyrzykowski is going to be talking about how the black hole Tom is rules them all. And
Hi. I think I cannot share the screen because someone else is sharing.
I just authorized. Oh, okay, that's
Okay, that's better. Thank you.
let me put you on the big screen.
And can you confirm you see my slide?
It says it's starting. Okay, there we go. Let me make you full screen and take it away.
Okay, thank you very much. So thank you for the organizers, Rachel in particular, for this opportunity. I'm an optical astronomer and I find other wavelengths quite challenging. But I'm going to tell you about the BHTOM, which we hope is going to be kind of one-stop shop, at least for the optical part of astronomy, and for the time domain astronomy in particular. I hope I'll convince you to that. But I will tell you a story. But before I actually begin, I will show some faces of people involved in this project. Fraser Gillan is sitting actually next to me. He's also listening to this talk, to this conference. So he's a new postdoc working on solar system objects. So you might hear from him on some other opportunities. I will also emphasize Priscilla Pesci, who is going to join us next month. You might be familiar with her name and face from LSST-TVS working group. But this is a group located mostly in Poland, but also in some other places. We have our own SPY in LCO, which is Katarzyna Kruszyńska, my former PhD student, who's working on microlensing with Rachel. Rachel actually asked me to give you a background of how we've been dealing with, here in Europe, I mean, we've been dealing with time domain, but also kind of broader networking of telescopes, and especially in optical and radio domains. So the history goes back to, at least my involvement in this project begins in 2012, where there was an optical infrared coordination network for astronomy. That was a large grant funded by the European Union, which was gathering the optical telescopes from around, which were connected to Europe. Simultaneously to Opticon, there was RadioNet, which was an equivalent in radio. And these two networks, they were functioning separately, However, in 2021, we started a joint project, which we called Opticon RadioNet Pilot, ORP in short, which was combining these two networks as a pilot, as the name stands. So we were trying to find some common grounds and share some experiences between working optical and radio domains for science. The ORP itself was a network of 37 partners. That's how we do it here in Europe with large consortia. And then there was 50 million euros spread over these people. The radio part was led by Anton Zensus in Max Planck Institute in Germany. Opticon part was run by Jerry Gilmore, University of Cambridge. The objectives, the primary objective was to provide the transnational and virtual access. So the idea was, I'll just I'll skip these letters and just show the map here. The idea was that Opticon was making the facilities available to people who otherwise would not have access to that. And the best example I typically give is that there is this Australian telescope, which is not Anglo anymore, is Australian telescope, which is typically not available to Polish astronomers, right? Like myself, for example. So through Opticon on ORP later, it was possible that we could apply for observing time at the AAT because essentially Opticon was purchasing a fraction of the time which was available at the AAT, and then through its own time allocation committee in Opticon, it was giving the time to people who put proposals to the Opticon or ORP TAC. So that way, some of the European astronomers with no access to telescopes, as you see the nice suite of telescopes listed here, they could have gained this access to these telescopes and use it for their own science. It was very similar within the radio domain, but I don't know that many details about the radio because that's not my domain, as I said. But anyway, it was also a network. This network was working together as well within the EVN, European VLBI network. But then, so you could also apply for time for these telescopes and have it paid for essentially through this European funding. On top of this transnational access, which was probably the main bulk of money was spent on this, there was also a virtual access provided, which meant that there were radio and optical archives available and also platforms. So for radio, there was LOFAR and Aperitif archives supported by these grants. And in the optical part, it was actually my domain. It was the BHTOM, where we were making the virtual access to a network of telescopes and coordinating the time domain observations. So I mentioned this here as the TOM toolkit was used to develop the BHTOM, which we have now. And it was all the development was funded through the European Union funding within Opticon and then later ORP. In September 2024, we started a new grant within Europe, which is called ACME, Astrophysics Center for Multi-Messenger Studies in Europe. It's quite a horrible name, I admit. And again, this is a consortium of a lot of partners, and they spread all around Europe and beyond. This is even broader than the previous ORP was, because this includes also institutes involved in multi-wavelength and multi-messenger astrophysics. That was the main goal of the project. University of Cambridge and NCBJ, I'm representing here in Poland. These were probably the only, and CFHC, of course. These were the only facilities and only institutes coming from the optical side. The rest was more into multi-wavelengths. So this is a gallery of what we combine within ACME. So it goes all the way from neutrinos, gravitational waves, of course, radio, X-rays, gamma, and so on. And it includes both radio and optical small and large telescopes. I will not go through this list. You can read that later in my slides for the interest of time. But this is just to emphasize that the ACME is currently the funding schema which supports the activities we do within BHTOM. Essentially, the operation of BHTOM is supported by the ACME grant, and we work in this environment of multi-messenger facilities, and we're trying to figure out the ways how to integrate their operability, how to conduct the follow-up is one of the aspects, but also how to maintain archives of data, how to harmonize the standards, and provide training to people. This is quite broadly how we can describe the goals of ACME. Okay, so coming back to history, I hope you recognize the spacecraft. So this is the Gaia space mission, European Space Agency mission, which was launched in 2013, and it stopped operating earlier this year. The main goal of Gaia was to observe the whole sky, 2 billion sources, map them, find the parallaxes, distances, proper motions. But as a side product, Gaia was reporting on things which changed on the sky. And this is the system we've built at the University of Cambridge, which was operating for the entire mission from the very beginning of the science operation 2014 until the very end in January 2025. We've been reporting on things which appeared, disappeared, changed brightness in various ways, completely agnostic to science cases. So we've been finding and alerting on these things as soon as possible. Because this was a Gaia space mission, so the typical delay was about 24 hours from discovery to the report. But anyway, at some point earlier in the previous decade, Gaia was probably one of the most productive provider of transient and alerts before it was, of course, taken over by newer surveys. So for that alert flow, we built the network of telescopes, and because Gaia was observing the whole sky, we had to build the network all around the globe to respond to these alerts. And at the moment, currently, this network has grown all the way to something about 130 telescopes with sizes from everything as small as 5 centimeter to 2.5 meter. Most of them, as you see, are located around Europe. This is of course, the geographical bias we have. But there is actually plenty of telescopes which are kind of left out. They're not involved in the main science anymore, but they're still sitting there. Some of them are still manually operated by students and so on. Some of them are robotic. Many of them have fairly good weather. Some of them have bad weather. Many of them were essentially volunteering their observing time because they were sitting there doing nothing. So we've gathered them into one umbrella and gave them purpose to follow the Gaia alerts. And this is a gallery of some of them. So what do we mean by small telescopes? It can be everything from a C-star with 5 centimeter all the way to one like 2 or 2.5 meter. But also we started expanding this network not only to professional observatories, but also reaching out to amateur observers because there is a large number of people with very nice facilities. And they have them not only in Europe, but they have them in Chile and Spain and nice places in the telescope farms. They can also respond to transients, they can respond to time domain targets, and they can provide scientifically valid data. So this is what we've been doing within our TOM, our black hole TOM. So what is black hole TOM? The name is essentially to be easily remembered and be catchy, but this is essentially one of the TOMs built on the LCO TOM toolkit. So this is a web page for the coordination, and we prefer to call our TOM as a coordination of time domain observations which we mean slightly broader than a reaction to transients. Time domain targets can be anything from supernovae, kilonovae, to AGNs, eclipsing binaries, microlensing events, whatever is time domain. This is what we can do with this telescope network. So of course it has built-in automated observation requests. And the main thing what it does, it processes the data from all these 130 telescopes. And then it does the automated standardization. Also, it queries archival multi-wavelength time domain photometry. And of course, we're expanding every time we are open to new users, new telescopes, and also new targets. I'll just quickly go through this schema, how we operate. This fits into some of the charts shown yesterday, especially by Andy Howell, that this is the environment we operate with. So there are these targets reported by surveys. For us, the motivation was Gaia, but then, of course, there are other surveys providing interesting targets. And then the users, through brokers in particular, they can decide what are the targets they want to invest the observing time into. And the request can be anything from like observing supernova or observing a comet or monitoring a quasar for 1 year. I cannot imagine a time allocation committee which would give you a 1 year of observation of one star. Yet, if you come to us, we will just observe it for you and we'll give you the photometric data for your object of interest, essentially with no proposal, with no issues. So all these requests, they go into our TOM system, BHTOM.space. That's an easy to remember web page. And then we take over, we communicate with the network of telescopes. I'll emphasize here that AEON is our preferred way of communicating with the telescope networks. But since we are working with a very heterogeneous network of telescopes, not many of them are like beautiful LCO with fully controlled, fully robotic schedulers and so on. But we are gradually encouraging our partner telescopes to install. Some of them are actually installing LCO's observatory control system, which has the AEON protocol built in. So we're getting there. Of course, some of other telescopes are communicated via email, for example, right? Which is still fine, as long as we can communicate with them in both directions. So both the requests and then the data from these telescopes, the standardized, the calibrated images, they go back to our system. We also query the archives, as I said, and this is what actually we bring back to the users. So we separate the users from the telescopes and from all the mess dealing with 130 different telescopes. So then the users can focus on publications. And because this is a TOM, everything can be scripted, everything can be automatized, and that's where we are heading. So I'll just focus here and emphasize the what's unique about BHTOM is that we can we have built in fully automated data processing. We do PSF and aperture photometry uniformly for all 130 plus telescopes. And then we standardize the data from any filter to Gaia synthetic photometry. And then the data is downloadable and it's science ready for everyone who's registered. I'll just show you a couple of examples. This is a supernova, this is a microlensing event. So these are the light curves we built from a network of telescopes. And you can't tell which data point comes from which observatory. That's our main goal and probably the unique feature of our system. Some other science cases. I will also show one case we did for the ORP project. We conducted some simultaneous optical and radio observations. So you see, this is the AM Hercule, very bright star, which was then observed simultaneously in radio and optical. That's actually how far we got between the optical and radio observations, because within the ORP we never managed to have the to have the radio facilities built into our TOM and make it operational. That's what I mean. We've been working on that, but it has never materialized into something operational. I will emphasize also the work by Fraser Gillan here, that we've collected data of the comet, and we managed to process it through BHTOM as well. So this is a work in preparation. And this is just a list of papers from very different science fields. That's what I'm trying to emphasize. There's not only microlensing, not only supernovae, but also young stellar objects and other weird time domain topics we can contribute to. And we include all the observers as co-authors, which makes them very happy generally. We also observe T Corona Borealis, of course, and it's not going to explode anytime soon. This is the overview of what we're thinking about getting into, and this we are of course in contact with Tom Toolkit people, but the plan here and the dream maybe is that we talk to other Toms, something what was missing, but there are tools now, as I learned here in this workshop, that there are tools of making the Toms talk to each other. So we hope that we will build that, and then we will also have access to the data. We're thinking about an archive of all the observations, because if you observe a star or a supernova, then serendipitously you also observe all the other objects in the field. This is the data worth storing and then using it for later studies. One of my last slides. I'm running out of time. I realize we also would like to add the kind of educational or citizen science angle to our work. And recently we launched a foundation which we called EAST, and our motto is "Where the Sky Begins." And this is where we use BHTOM as the main platform for communicating not only with the professional astronomers with telescopes, but also with people who own telescopes, but very often they don't know what to do with them. And these telescopes are modern. They have modern CMOS cameras with filters and so on. So we help connect these telescope users with scientists, and hence we can gather even more data of time domain targets. So this is what we're trying to facilitate through this foundation. I'll just mention the workshop we've been organizing with Gaia as the main theme, of course, over the last 16 years now. And the next one is actually the very next week. So if you're interested in listening in, there is still possibility to register for online participation. You can check what's going on in this field, what our network is doing, and how Gaia alerts in particular were taken care of with the telescope. So I'll stop here, and thank you very much.
Thank you very much, Lukasz. And I will invite our next speaker to be setting up. In the meantime, we have time for one quick question.
Hi, Lukasz. This is Griffin Nessenbada from UCSD. This is like incredible what you've done, I think. I have at least a few questions, but I probably only have time for one. Okay, so one question is, if you're already making all of this photometry, essentially, you're a producer of photometry. Have you thought about sending that out over Hermes or something as like photometry alert that somebody can subscribe to, and use that as a way to get into other people's toms?
I'm not sure if I got the question, but you're asking whether we consider sending the data out to other toms, you mean?
Yeah, that's right. Sending it out as an alert stream.
Yeah, well, we have everything, there is an API to everything in BHTOM. You can write your own script. So if you can do it yourself, or we can set it up, right? So you can do it either pull or push. Yeah, so it's there. The functionality is there. You just need to tell me who's interested in what, and we can set it up. I'm happy to talk about this.
Right. Yeah. I mean, actually, that's true. That's a way to do it too. But I guess the point is, I don't know when you have new photometry, but you do. So you could just send it to me whenever you have it. That way I don't have to check every 5 minutes or something like that.
Sure, no problem. Yeah.
Great.
Okay, thank you. Let's thank Lukasz one more time.
Thank you.
And now we have Poonam Chandra, who is going to tell us all about time domain, efforts in time domain in the radio domain.
Thank you so much. Thank you, Rachel, for having me, and good morning, everyone. We had a very nice overview from Nayana about multi-wavelength and the need for multi-wavelength to do science, because at the end, we are here to do science with all these means of doing science. So I'm here to focus mostly on the radio bands, and the landscape of radio transients is slightly different than other transients. One thing is clear, that radio transient sky is almost always dominated by non-thermal sky. So non-thermal emission is dominant, and in that, whether the electrons decide to do incoherent emission, which is mostly synchrotron, or they try to emit in unison as coherent emission, which has almost always very high degree of polarization, and these are very slow and
The
very
slides
fast.
are visible on Zoom. If would it be possible to share the slides on Zoom?
Am I not sharing?
Let's make sure.
Now we see it.
Okay, good.
Sorry about that, folks.
I should have paid attention to it. So anyway, I will repeat just a little bit, which is important, and that's coherent versus incoherent transients. And this line determines, on the left side, one sees coherent transients, on the right side, incoherent transients, and one of the way to distinguish is brightness temperature. And since this is not a radio heavy community, let me just say that brightness temperature is that, I don't know how to put it, a fairy tale concept, where if you take that the source is emitting black body, then what temperature that black body will have. So that's probably the best way to describe brightness temperature. I really like this slide where Dale Phil puts all the transients in these categories, coherent, incoherent, galactic, extragalactic. Let me just say that we are yet to find dragons, but rest of the things we have found, many of them. But I'm going to focus on the top. Right, I saw that falling, but anyway. Top incoherent long duration transients, because that's where most of the multi-wavelength efforts are going to come in picture. These are mainly three kinds. One is gravitational collapse, which we see in supernovae and many of these F-bots kind of things. The nuclear supernovae, where actually radio can be very important in determining between single degenerate, double degenerate model. And recently, 2020 EYJ supernova was seen in radio band, and we have a pretty good idea of what kind of problem it must have had. And then the central freezing event transient, which is gamma ray burst, merger of compact remnant, which could lead to many different kinds of transients. But radio is absolutely essential, because in this case, one of the things we have seen, this is again, everybody talks about 1708-17, but nobody has shown this slide, so I can show that. So this is radio observation when the optical and high energy world sits quietly, we come into action. And when we observe, we come 75, and every 30 days, we actually see the jet moving the supersonic speeds. Before these radio observations, it was not even known whether the merger of neutron star gave, we knew that it gave rise to gravitational wave, but we didn't know if it gave rise to gamma ray burst or not. So this kind of confirmation came from radio bands. Other thing is that we do believe that as you have bigger and bigger neutron stars or neutron star black hole mergers, you will have little kilonova, so less of optical emission, infrared emission. And in that case, radio will be the only way to identify the properties. So radio has a very important place in multi-messenger astronomy, and we're trying to understand that. All right, so I work at NRO, so I'm here to talk about NRO, and our mandate is to run world-class radio facilities and make research happening with these telescopes. So we have several of such telescopes. First is like Big telescope, which is 100 integration, West Virginia, and it is it's been working for decades now. And it also has, the site also hosts some smaller telescope More important is UV 20 meter, which is part of Skynet, which we will hear tomorrow more about. Since I already said that, and since it's not a radio crowd and there are some grad students, I did add some slides this morning, and I wanted to say that it's a 100-meter telescope. It's not easy to build, but you need to build big telescopes in radio, because on the left, if you see moon with a 300-meter telescope, that's how it looks. And if you see the same moon with 10-centimeter optical telescope, that's how it looks. If you need the same sharpness at radio wavelengths, you need to have a 30-kilometer telescope. You don't get to build that. So what we do, and that's where the concept of interferometry and aperture synthesis comes. So that rather than building this one 30-kilometer telescope, we build a lot of smaller telescopes. Smaller here also, like 20, 30-meter telescope. But even this is super expensive, and that's where we take the help from aperture synthesis. So we just build some telescopes, and we assume that within 5 hours we are looking at that source. And since Earth is rotating, it is kind of giving the stamps of or fingerprints of different. It's filling up that space, that big mirror we need to fill. And that's what we do in radio interferometry. So after this, I have to show this slide because I have been showing in a lot of outreach talks, and this is an inside joke among radio astronomers that this was wrong, where Jodie Foster was listening to the signals from alien. This was wrong because we don't get to see the sky in radio band. We see the visibilities. Visibilities are, we collect voltages from different antennas, and we cross-correlate that, and then we take the inverse Fourier transformation of that. So it's called synthesis imaging for a reason. And so I have to say that if that's how your sky looks on the left side, your data will be in these amplitude and phase, and by no means looking at the right two plots, you can say that you are seeing the left side image. So you really have to analyze the data. But I think when Nayana was giving the talk, and it occurred to me that actually this is not a correct story. This is correct. You know why? Because Jodie Foster had a team of grad students working on the data in the control room, and they were telling her on the continuously whether a signal is detected or not. And one grad student told her, and that's when there was a hurrah moment. So maybe, that's the other side of the story. But jokes apart, radio band. So on this, this is how actually a real data looks for that's right inside the sky for a point source, and the bottom is the not so point source, and you can see the amplitude in phase with respect to UV, which is also a new concept for non-radio astronomers, but it is the antenna distance projection of antenna on the ground. This is how it looks. So this is basically you have to go from left to right, and it takes some time in radio astronomy. And whatever we are trying to build, whatever we are trying to incorporate, automation, we have to take into account these kind of things because this is important. So on the same note, we have this interferometry telescope, VLA, the Karji-Jansky Very Large Array Telescope. It's in New Mexico, which works in 1 to 50 gigahertz, and I think all radio astronomers in the world have been using this and making these discoveries. VLA, the good thing about VLA antennas is that it can give you multiple configurations, because if you can see there is this strange tracks where the antennas move, and you can see the tracks here a little bit, and they give different configuration. A is the highest resolution configuration because the antennas are 35, maximum distance between the antenna is 35 kilometers. So your lambda by D is lambda over 35 kilometers resolution. The D configuration is all the antennas are within 1 kilometer. So that's a very compact configuration. So our gentleman with D configuration, if you look at the bottom right image, with the VLA configuration, that's how he will look on the left side. When you have only the compactor, you will miss out the fine structures. If you have only the A configuration, you will only see the structure. You miss out on the the extended emission, so you won't see the full picture. So it's difficult to make images in radio astronomy. So just to show you that when I took VLE configuration and GMRT and very short observation, and you are still, now you're able to make some picture out of it. Now if you make observations for some more days and have a better UV coverage, you will have better replication. So this is how radio astronomy works, and VLA has been doing that for a long time, and extending the concept of interferometry, we actually put antennas in different the states of UVs, and now we get a much larger baseline, and so your D increases by thousands of kilometers, and one can do observations which have resolution much better than optical astronomers can do. And this is why we could actually see, when we observed on 2 different days, we could actually see that the shock had moved by, in these many days by that much distance. This is real data on the left-hand side. And that tells us that it has to be moving with 99% of the speed of light. So this is possible with VLBA. We also have ALMA, which is the millimeter band in Chile, but it has collaboration with Europe and Japan. And so US has 1/3 of the time, and also the responsibilities, and it is at very high elevation because water vapors become important at millimeter bands, and we have to take care of that. So that's why it is important. ALMA works in millimeter band up to around 1000 gigahertz. So it is very important for exoplanet rise and molecules and astrochemistry. We are planning ALMA upgrade by sensitivity increasing by factor of 10. Next generation VLA has gotten seed funding, and we are working on that, and it's planning to that we will replace VLA and VLBA with NGVLA. The initial work has started, and the idea is to start with the VLBA kind of array, starting with 10 antennas, and then slowly work up to 200 plus antennas as it was initially planned. So that's how the plan is. But once we have NGVLA, we will be able to discover 1708, 17 kind of events up to redshift of 0.1, 500 megaparsec. So that's going to increase the phase space by a bit. Now, NRO's role in time domain astronomy, a very quick slide on circuit. We have been having a lot of I would say surveys to discover radio transients, but and even the NGVLA is going to have those kind of surveys. But I think NRO has clearly mentioned in time domain astronomy, we are going to be focusing on the follow-up. That's where the multi-wavelength comes into picture. So our more efforts are in this direction. And that's because in the past, so many radio discoveries in transients have very important inputs from radio, and it would not have been possible to know the nature of these sources without radio bands. That is no doubt true. So here I'm just compiled most of the radio, like NRO's radio telescope, along with telescopes which are focused on transient astronomy in multiple wavelength, and you can see that NRO telescopes will be a kind of trying to, will be overlapping with many of the facilities, and they're going to make very important discoveries. And we have to just fine tune and find better strategies and try to optimize the time domain science with NRO telescopes. And with that, we did form NRO Time Domain Advisory Committee 1.5 years back, and we realized that that the days are gone when you will find 30 supernovae in a month and then find 3 good supernovae and put VLA on that. You're going to find millions of transients, as everybody has been saying. So we cannot put our telescope on every transient for sure. So we have to find what are those 1% of good transients, and which we should be doing, and how are we going to do a most efficient way of doing science. And we do realize that lot of proposals and data it becomes a very complicated system. I was giving a little bit of hint of that in the unconference session, but But the idea is that data needs to be there for one to do science. And also people should get credit to do science. So with that, one of our idea is that we have actually started, and we did give this recommendation a few months back, but it has not yet been implemented, but we propose what is called user trigger observation in the current NRO system. What that is that if an interesting transient happened, you fill out a form as long as your observation is less than 1 hour, which is not too much of time, and less than 15 gigahertz, the weather is not really very important phenomenon. You don't have to do pointing. Just fill out a form, give like 4-line scientific justification, submit the form. It goes only through the conflict checks. Conflict checks means there should not be an approved TO for that particular source. And we don't want to, we don't want to remove the TAC approved proposals. But if there's interesting transient, it just goes in the queue, scheduling queue, because we have dynamic scheduling for years now. And it gets observed on the priority basis. Images are made, preview images. Data are for everyone to grab. We don't put proprietary because it has not gone through any science verification or scientific, any tag. The idea for this is that, with one data point, you can put out circular, but you cannot write a full-fledged paper. So as a grad student, you still have your data, but you don't miss out that important data point when the science is very important. And the thing is, one thing we have to remember is that radio is a non-thermal sky. It's synchrotron, power law. So it is almost always going to be log cadence. What that means is that within first 10 days, you need data on day 1, day 3, day 5, day 10. And then you need data on day 10, day 30, day 50, and day 100, and then day 100 and day 300, and so on. So it means this first 10 days become very important, crucial to get the data, but not good enough to get a peer-reviewed paper. So, it's the best of both worlds. So we did recommend that let's start with small time allocated or reserved for this, and we see how it works and how much work it is on an RO system. So I'm hoping I'm going to push for this, and other things took priority. So it kind of is a little bit in the backseat right now for an RO. The other things for NGVLA, we are working, like NGVLA is to come online in next 10 years, but we are working really hard, and we have this whole time domain narrative where we are we're working on this premise where it's transient event and trigger response time, like less than 1 day, like 1-2 days, and less than a week or so. And what we have come up with is the third category, rapid response filler proposal. So what that is, we realize that in some cases the transient, it's a little bit like UTO, user trigger observation, but it's slightly different. Is that, again, it's a web-based form. Whatever you want to observe, it's a transient. You actually give just the basic parameters, and you also give what kind of range of angular resolution. Remember, the NGVL is going to have 200 antennas. So one has to remember that even if some antennas doing some observation, some antennas are doing some observation, maybe there are 6 antennas which are available. And we can choose those 6 antennas, see whether it's going to match this angular resolution range or not. And we just put out antennas to do that transient science. So again, since it did not go through peer review, scientific review, we are no proprietary data, but we give you data. If you want data, we have data. So that's the concept of this. Hopefully this will be implemented in NGVLA. So these are 2 major things which as Transient Advisory Committee we have come up with. Now integrating radio telescopes, let me see how much time do I have. 1 minute. No. Okay, very quickly. All right. So anyway, I just wanted to say that, of course, AEON has shown with 2 very different systems, Gemini and Soar, how it's gonna, it can integrate with different system. And VLA and GBT already have dynamic scheduling. So, and we can work with scheduling blocks at very quick response time. So I think it's going to be not very difficult to integrate this facility. And one still writes the proposal as one's gonna write, and then, but the problem with radio astronomy is that we have to, look for the right time, set time, and then prepare a scheduling block, and then send the mail and wait. And if it can be done in an automated way, nothing better than that. And I think that's, we are already talking about, and I think it doesn't look very difficult because we already have a lot of things which are already in place, which is required for these kind of observation and integration with AEON+. Some of the things we have to take care of, these things are which are not probably in other bands are have already listed here. But some of the, and other thing is that we are not so pressed for time in many of the cases, because as you can see, the radio starts much later. This is again the gravitational wave event. So maybe it's not that, critical in many cases. Of course, in some cases it will be. The pros are that we don't care for day or night as long as we have the sources up in the sky. And of course, flexible dynamic scheduling. One thing I just wanted to say is that NRO is already building telescope time allocation tools. The idea is that if you have a science idea in your mind and you know which telescope you want to, we will give you a website where you can convert your idea into the resource request with everything you take into account. And it does have time domain constraints also. So these are Ali's slides, and I would request, she's better place to answer the questions. But the thing is, it starts from solicitation stage, and you get the finally, data just on that one TTA tool concept, and it's going to take 2-3 years it's more to mature, but this is, it's going to be really important. And AEON Plus should think about how it can develop APIs to talk to these TTA tools. Because Skynet, I think I'm going to skip because there's going to be a talk tomorrow. But because GBT 20 meter is part of Skynet, so we are trying to think more science with that. But I did want to mention that please also think of other telescopes. For example, DSC 2000 is going to be an interesting telescope. It's going to scan 30,000 square degree of sky 16 times in 5 years. I'm going to find many transients and also going to follow up a lot of interesting transients and very sensitive telescope. This is my last slide, and I think I just leave this thing and take any questions.
Thank you very much, Poonam. You set us up for the next discussion perfectly, so I don't want to rush you there. Before we move on to the discussion, do you have any questions? No, there are any hands up in line. I have one. You mentioned at the start of the complexity of the data reduction for it. Can you speak a little bit to how the data reduction is handled? Is that done by an AEO? Is that end user? Are there public tools available for that?
Yeah, so I can say a little bit on that. So NRO has always, NRO has developed softwares for this, and CASA is the software which is publicly available and is used to do data analysis. And for many, many years now that NRO has its own pipeline to calibrate the data, because calibration of data is very difficult. So it does calibration of data, and calibration of data also, one has to remember that if you're switching on a television next to our radio telescope, you're going to spoil our data. If you're looking at your cell phone, you're going to spoil our data. So we have so many practical aspects which we have to, we can't ask people to stop living their lives, but we have to take, those things from our data. If a satellite passes by, we have RFI, radio frequency interference in our data, and these are like 1,000,000 times brighter than the real signal we are looking for. So editing the data, flagging the bad data becomes really, really important in radio astronomy. So we do have softwares, and people are improving those softwares. Every single of these things are publicly available. Now we have, NRO has this policy that if your observations are made, they do automatically calibrate your data, and they have this QA score. quality assurance score and QA pass and fail and further scoring. So that decides whether your data is usable or not. And at lower frequencies, many times data are not usable because ionosphere becomes important factor and other things. And since we are early in the discussion session, so I have to just say this little bit story about how radio astronomy is done. That in maybe more than a decade ago, GMRT was shadowing these FRBs with Parkes telescopes, and at that time we were writing a lot of papers because it was initial phases of FRBs, and then we found that there are galactic counterpart of FRBs, which are peritons, and we wrote papers on those. Until one day somebody found that all the peritons are found on weekdays and none are found on Saturdays and Sundays. And it turned out that when people heat their coffee and they open the microwave, suppose you set it for 30 seconds, you open up for 29 seconds, there is a spark comes out and a signal also comes in Parkes L-band feeds. And that's how we were discovering peritons until we did this experiment and then we figured out. So I'm just saying that that makes it very difficult to do radio astronomy because we really have to take care of everything.
Wow, that's something to that's an calibration for everybody. Let's say, I'll do it one more time. So now we go to the discussion section and I will,
I'm Chris McCully. I'm at Los Angeles Observatory. I'm studying between supernovae science and pipeline and things like that. So I'm mostly optical in terms of astronomy, so I'm just facilitating one. So I'm going to try to ask questions, but I'm not expecting to lead a lot of the discussion. So we've been charged with, I'm going to read it just again, make sure. Okay, so we're trying to talk about AEON-like observations with radio and submillimeter facilities. We've talked already about some of the science motivations. We can talk more about those if we want. I am thinking that for this audience, it may be better to talk about what are kind of the technical constraints, limitations that we need to develop to make this more possible. So the first question I'm actually going to ask is for those of us who are not experts in submillimeter versus radio. Nayana, do you want to say a little bit about the observing differences between submillimeter and radio, or like what are the different constraints we need to think about?
Yeah, sure, I can talk about it. So when we do coordinated millimeter, centimeter, and sub-gigahertz radio observations, what becomes critical is the weather condition in the site of sub-millimeter telescope. Because if the weather condition is not favorable in the millimeter bands, the data becomes completely useless. So any scheduling constraint has to be tied with the millimeter band facility to begin with. So for instance, what decides when to get on target is ALMA or NOIMA rather than VLA or GMRT or other low frequency telescope. That is the main aspect when we have to get sub-gigahertz to millimeter band near simultaneous observations. Second thing which I found would be very beneficial is to have a coordination between the facilities without like the observer or the external person trying to get in touch. For instance, if ALMA can directly communicate with the other coordinated facilities that this is the site, this is the condition in the site, we are okay to get on target in next few hours. If this is coordinated internally, it would be very, very beneficial. Because for instance, when we did this exercise, it was almost bugging people at odd hours because I want the observations to happen at the similar time, but my OE is sleeping in Australia. So, and also it was like back and forth going because we were ready with all scheduling blocks, getting observations done on a particular day. And then in a couple of hours, I got a message from the ALMA OE saying that it doesn't look like we can get on target because the sky conditions are getting worse. So probably we are holding the SB. Then I am contacting every other 3 observatories which are ready to observe saying that please hold the SBs because the sky is not great, we can't execute. Now, these three are all disruptive TOs, which means that when we ask for trigger, the existing schedule is disrupted, or some already scheduled observations are moved to a different slot. So for example, at least for GMRT and ATCA, these are done manually. So the scheduler or the OE is trying to contact the other PI and say that, in fact, I contacted Poonam for WPP saying that I need this slot, it's your observations schedule, would you mind moving it to a different time? And I am finding the different time where Poonam's object is on sky and keeping the scheduler in loop, saying that I talked to Poonam, she's okay to move it, can you please move it and schedule my observations on that day? So if at least to some level I understand that it is difficult to do this like in real time, but at least a part of this, if can be coordinated between the facilities, it would be really helpful in the future. Yes.
Back. And so just to summarize that, so it sounds like, okay, weather is one of the main constraints you have to worry about for submillimeter. That's not such an issue in the radio, is that right? Okay, so weather is different issues, but there is still weather. I've asked Joey to kind of try to capture like some notes on all this, so I appreciate that. All right, Juna.
Hi, everybody. Juna Kohlmeyer. I am I'm primarily a theorist, but also the director of SDSS-5, which is an optical all-sky facility, optical and infrared. Okay, so I have a few questions about the radio and submillimeter. So one is, in terms of if I'm just wanting to look and see whether the conditions are good at all of these different sites, I can, there's no, like, for example, with LCOGT, I can see what things are online. There's no such interface that exists right now. Okay. Two, yes or no? Okay. And the no for the some telescopes, no, is a technical thing, or is it they don't want to cooperate, or is it political?
Or is it just effort? Yeah.
GMRT and ATC, I believe, since they are fixed schedule telescopes, you have them online. You can see and then you can choose your white slot. But VLA works on dynamic scheduling, so because, when the weather is good. So VLA, the people don't know when their observations are going to be scheduled, so it's not online. So
okay.
That's the reason.
Okay, and there's not a huge network of amateur radio telescopes out. Like you're not really connecting with the ham folks to get, okay. And that final question, sorry, I know this is just for my benefit. I'm just learning. I'm sucking information out. You said you made a bunch of recommendations and they weren't accepted yet.
Our committee did make the recommendations, but then I would say the scene of research and things changed and it kind of took a back seat. It's not that it was rejected. It's just that we haven't yet come back to this because it does need extra resources, and right now we are struggling to find some funding for those things.
Okay, but that's the bottleneck, is finding resources and time. It's not that people are against it necessarily. Okay, and my final question is, when an optical, what if the TOMs, that the optical or infrared or TOMs are triggering, okay? For the submillimeter and radio, one of the benefits is that, you got some time, right? It's not like, get on this right now. You don't have to do the ambulance chasing that we do in the optical. Do those targets and various brokers actually come with a expiry? So in other words, like, if you don't get on this with one of these radio or submillimeter telescopes, don't even bother. Is that something that's built in on the faster, on the faster time scale kind of broker side? And that's for everybody, not necessarily for you guys.
I can answer this because when I raised my hand, my also question was dependent on that. So one of the difference based on millimeter and centimeter astronomies, also the thing is, when you do radio observations, you just don't see the synchrotron emission or non-thermal emission. Since absorption goes as lambda square, radio is also absorbed in the beginning. So even if I'm putting, say, VLA on a source, and I don't detect it, I don't know it's not detected because there was no synchrotron emission to start with, or whether because it was absorbed. And that is a very critical science, because synchrotron emission is not an easy emission to be produced, because you have a 511 kilo electron volt electron, and you have to bring it to 1 GeV acceleration to bring out emission in centimeter band, 20 centimeter. So in that sense, millimeter astronomy becomes very critical, because you have much less absorption, again lambda square. So you do want to get on ALMA first or NOEMA first before getting into the GMRT or VLA or other those kind of telescopes. So there is, I would say, in millimeter band, there is a critical window, but again, it's not set in stone, because you may not be able to accelerate electrons to that kind of energy that it will ever emit millimeter and, escape. Yeah, exactly.
But I think in terms of the practical matter of actually getting a network system where you can do the simultaneity kind of observations, or if not simultaneity, sort of in relevant timescales. And this is definitely something in our program, which is just optical and infrared. It's not radio. Our targets all have, various expiration dates, essentially, because at some point, if you didn't get on them within a window, you've missed the physics or not, right?
Yeah.
And I don't know if the community has integrated that.
No, in radio, we can still sleep through the night and do our observations in most of the cases. But there is some, but we kind of, optical does give us a good sense of that, like fast blue optical transients have a very fast evolution stage in optical. So in radio also, we tend to see them that, you need to get on early and those things. But type 2 and supernovae, you can still, do it after weeks.
Yeah, we have a comment online. Go ahead and unmute and go ahead.
Yeah, hi, this is Mark Kerwell again. I just wanted to speak to the submillimeter or millimeter observations, and there's no technical challenge with knowing what sites have what weather. It's just that generally, I would say, at least originally, many of the millimeter facilities started as university projects. They've started only very recently becoming more national projects, like with ALMA or NOEMA. And the development of coordination between these facilities is much less developed than it used to be, that it could be. And it's not that there's no willingness, and there's not even really a technical challenge to doing it. It's just sort of a political and an energy challenge. How much time do we want to put together to doing these coordinated types of observations? It can certainly be done. We've done coordinated observations with NOEMA and ALMA and the SMA, where we've all observed at 1.3 millimeters. And when one telescope can no longer see the object, the next one picks it up, and we keep going, and we can get nearly 24-hour coverage on any particular source. But it does require not just communication, but also sort of coordination at the kind of observatory planning level to do these sorts of things. It's much harder to do that on a very rapid turnaround TOO. Again, I talked about this yesterday. One way around this is to have sort of pre-approved projects, which we do at least at the SMA. They're working on these, it sounds like, at NREO facilities, and I don't know about NOEMA specifically, or even the single dish millimeter facilities, like the ERM 30 meter or the LMT. But again, it's not a technical challenge. It's not even a willingness challenge. It's just sort of we're behind in the development of this coordinated observatory view.
Yeah, it sounds like to me like this is kind of where the optical community was about 10 years ago. So yeah, no, I think this is very common. Yeah, go ahead, June.
Yeah, so that's I think a framework that I like to think about is, Cat 1 hard, Cat 2 hard, Cat 3 hard, where Cat 1 hard is primarily an issue of money and organization. Cat 2 hard is, well, you have some real technical challenges, but you think you know the way forward and you kind of have a good idea. And Cat 3 hard is actually there's some breakthrough in physics or in our understanding that needs to happen before you can make it, happen. And this sounds like Cat 1 hard, which is good because that means you can throw resources at it and solve it. And a question I have is whether at the national level and at the, maybe international level, now assuming steady state, which we're not in, of course, but I'm a theorist, is there any kind of, hey, we've got this Rubin Observatory, we have this network of telescopes, we have LCOGT, we're going to actually have a key project focus on FBOTs or focused on blah, 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 like where it's actually organized at the national level where those resources are designed for simultaneity of observations or actually, improving that networking. Like, is any such program being recommended or implemented?
Actually, I'd like to jump in on that one, if I may. There's kind of a chicken and egg problem in my perception of this, in that the community certainly has the science drivers. We've had a number of different talks telling us about the science drivers. And there's the desire in the community to have that opportunity, but they don't know what opportunities to apply for other than we have to submit these double jeopardy proposals into lots of different opportunities. And then again, there's from the observatory side, what I'm hearing is, well, we need observers to put in proposals, so we haven't put together the opportunity to propose for. So that's kind of the point of bringing you all here, is to have that discussion and to say, what do we need to craft? What opportunities should we put together? How do we coordinate the science community to put such a proposal together and coordinate that with the observatories to make sure that the resources are there to propose for?
Yeah, so thinking in terms of the workflow a little bit, I want to dig in on a little bit deeper on something you said, Nayana, that so you showed the forms you filled out, for example. How much of those are just template boilerplate that you could, like, I mean, the root of my question is, how far away are we from being able to have someone like me be able to trigger observations? I'm like, oh, I've got an interesting supernova, I want to trigger observations, where I don't have to have a really deep, intricate knowledge of the instrumentation.
From my experience, it's quite difficult if you are not an expert, especially, for example, ATCA, I realized only when I had to deal with this object. As I mentioned, I realized that you have to learn to observe. There is no observer, like there is no technical staff in the observatory throughout. You are assigned a observing expert whom you can ask for assistance, but you are in charge of observations. You are basically steering the telescopes and getting the initial setup done. You are responsible for not crashing it on the ground. So it's like completely on you. So like, to do that, I have been doing radio astronomy for the last 10 years. Like, my entire life is looking at visibilities. Even then, I found it a little bit challenging because the load of being responsible for the entire 8 hours of those antenna. My OE was extremely helpful and supportful. He was online on Zoom call, but I am steering the telescopes from Berkeley. So it's quite far from a fully automated setup is what I feel. And also the difference in way observatories operate. For example, like GMRT doesn't have a dynamical scheduling. It's like when the person in charge is in office and responding to your emails is seeing the white slot request and saying that approving it. So once you skip that 8 hours, local office hours of each continent, you have to wait next 24 hours. So to get this SCD, you have to basically keep on checking your emails like throughout like 48 hours and make sure that everybody responds. So you immediately respond back saying that this is the time window I want, or this is when we need observations. So for instance, GMRT has to change the scheduling to a dynamic or much rapid response, which is I would say, bigger decision from the entire observatory. They have to set up new tools to implement that change. So it's not very easy at the moment. I think a few years.
Yeah.
I would like to just comment that alone is a very observatory specific issue. It depends on, the complexity, or if your observations are queue driven, or, dynamically scheduled with operators that do the heavy lifting. At the SMA, if you have a pre-approved project, all you need to do is email the coordinates and everything else is taken care of.
Okay, so it sounds like it's kind of like the optical observatories as well, I think still, is that, there are still observatories that you fly to go actually operate versus, ones that you can queue schedule like LCO. So I think there's a wide range is the short answer. Okay.
I just going to add that like Nayana is correct that for a long time, this is how radio astronomy has worked. And that's why we have had a very small set of astronomers. But now we are trying to change, for example, in VLA UTOs or rapid rigor, we are going to give you the template scheduling blocks. And you have to do is like 4 lines of scientific justification and target coordinates. And we're also going to give you the preview images. And also, so in that sense, it's kind of like just give the coordinates and very small science justification like Swift XRT, and then you get the image of yours. So we are trying to adopt that model.
So fundamentally, it's not necessary that there's a fundamental need that I wouldn't be able to observe something. It's really just the current state of tooling that exists. Okay.
So I'm approaching this from a TOM toolkit development perspective, and there's 2 things I've heard. So yeah, supporting radio observing is great. Yeah, we want to do that. But when I hear, oh, we have a web-based form, or, oh, you just send us an email, what I'm really looking for is an API that I can talk to, and that way I can help Curtis when he does solve those other challenges. I can just reduce the friction for him. So yeah, let's think in terms of APIs and not web-based forms or emails. Yeah.
So, okay.
Hang on a minute.
Yeah, so we need the mic so you can hear online.
I just want to echo that, because I do think that you don't want to take all the steps that the optical community took in the last 10 years to get kind of everything. You kind of want to take advantage of all of the mistakes and then all the development that was made and kind of just absorb all of those tools immediately and kind of skip some of those like web form, email kind of things. I think that it sounds like a great opportunity.
So I mean, so that sounds great. I mean, this is really good so far. So I want to kind of step to the next part of the workflow. So now I've emailed the coordinates and the observations are happening, whatever happens. What is kind of standing in the way from being able to just automatically turn something into like something I can send as like a TNS report or something like that? What are the challenges? I mean, you mentioned this briefly. What are the challenges in reducing the data and turning it into something that, again, say we're in a collaboration, you set up everything at the beginning, and I find an interesting supernova. I click the button, and you're still asleep in Australia, and I want to submit the TNS report before you wake up. What are the steps that we're missing to be able to do that?
So the major roadblock is the data reduction process. So there are certain observatories who gives you science-ready products like ALMA. So once the observations are done, within few hours, you can download the images. Anyone can measure the flux densities and send a TNS. It's very easy, but it's only ALMA which does that right now. NRAO for the VLA, they provide calibrated visibilities. Still, one has to run the imaging and find the flux measurements, which is not that difficult. But for all the other observatories, like all the centimeter observatories, like ATCA doesn't have a calibrated measurement set which they provide. It's the raw data that you download from the system. You run the calibration and data reduction, which a non-radio astronomer cannot do. Same with GMRT. You have to do the reduction, which is a tedious process. Like ALMA, Meerkat also gives you science-ready products at low frequency bands, which is essentially you download the FITS image and send the TNS. Did that answer?
Yeah, I think so. So, I mean, again, it sounds kind of like where the optical community has been, except that the number of people who understand the data reduction process feels smaller in this case. Yeah, go ahead.
Again, since I'm representing NRAO, I do want to add that for NGVLA, we do have a mandate to provide preview images within 1 hour of observations. Yeah, so we everything goes on priority basis. So we are giving a priority A to all the transient observations. So so that's one thing. So you will get images. Second thing I wanted to comment on your your thing is that actually 1.5 years back, I agree that we don't want to reinvent the wheels, and we are making mistakes. And for that purpose, at like 1.5 years ago, I reached out to around 50, 60 people in the community, and I wrote emails, including Rachel, that what do you expect from us? What should we do? And since you happen to be talking to the chair of the Transient Advisory Committee, that's me. Please, 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 please write to me what do you want. And because we really are looking for these kind of feedbacks, and I can tell you that I don't know all these nuances, and I will really benefit from knowing all these things. And we'll bring out to our advisory committee and discuss with them and take these things into account. Thank you.
That sounds like an unconference session to me.
All right, go ahead, Gina. Okay. Well, so one of the other technical questions I had in this is, so I mean, because you're dealing with visibilities rather than just straight pixels, your data volumes can be pretty large. Is that right? So what is, like for, say, an average submillimeter and an average radio observation, what does the data volume look like for one set of observations for one object?
GBs at least. We're talking about a few tens of GB at least for an hour or two. Yeah.
Yeah. What about for radio?
It's roughly the similar size, but I do want to say the following, that, you know, there is a good news here. We are dealing with transients. These transients are point sources. So the complexities of radio data analysis and taking big data and doing the polarization calibration, scanning through UV coverage does not apply. You can have very small data point as long as you meet the sensitivity. So then it's not that very big.
But if you're doing the data reduction, your best bet would be to have the data reduction close to where the data is taken, because transferring tens of gigabytes around the internet is still a bit of a limitation. So we're ramping up, so I'm going to take prerogative a little bit and ask a little bit more about, so there's been things like Chime, who's been interested in these FRBs and things like that. Can you talk a little bit about what their strategy has been? They've been kind of a small collaboration with a very dedicated group to try and do all of these cross wavelength observations. Can you talk about what that entails?
Again, I don't know that much about Chime, but I want to say that Chime is dedicated towards a coherent sub-second transients. And in radio transient, there are two kinds of transients. One, what we are talking about, which are image domain transients, which is you make the image and see whether you transient. And then these are time series transients. You just take the time data and then you look. And so Chime is completely dealing with those time series data and looking for these millisecond transients. And they are, and of course, everything is, you know, they are making it public and they're looking at the data. But I don't know what else you want to ask. But this is a very different strategy then.
Oh, absolutely. But that's why I wanted to kind of put it at the end of the discussion is, you know, this is a different strategy. This is kind of flipping the question on its head. we've discovered an optical transient and we want to trigger submillimeter radio observations. This is kind of the opposite. I've discovered a radio transient and I want to get other wavelength coverage of that transient.
Yeah, but it's the similar thing within the chime. I don't think they have a very good localization, but whatever localization they have, as soon as they put it out, one can start the observations. And we have done, so in that sense, it doesn't matter where the transient comes to us. The strategy kind of remains the same. As I said, in the past, we had been shadowing with parks to see whether there is some kind of afterglow, but we didn't find any. So, but those things remain same.
But when you're talking about like very short transients like this, I mean, then we are back in the regime where we are ambulance chasing, as we called it, right? And so how did they go about getting the localization fast enough that we can get on it, say, with other facilities? Is it only doing shadowing observations, or is there a way to do the reduction fast enough to get the localization and then push it out to the community?
So my understanding is that you only in the repeating FRBs you are able to do that, those kind of chasing, and many times they have these persistent sources, and you kind of look at those sources and try to see which part of the galaxy they are and what are they doing properly.
Yeah, I mean, that's definitely like the most extreme case that you really do have to be shadowing. That's when seconds count, and there's no way, like we're just really, really far off on that. So that makes sense. But I was wondering if there is are there other radio transients that people would be interested in? Like if you detected, I guess the physics typically dictates that the radio comes later. Is that right? So
radio does come later if it's the afterglow or if it's the incoherent. But if it's coherent, like as FRBs are there, or even in magnetic massive stars, we see this electron cyclotron coherent emission at magnetic nulls, or even brown dwarfs, you see this coherent emission. Those things are more transient but persistent, but they are not explosive transients. So that's very different ballgame.
All right. Well, we're about out of time. Are there any other things anyone online or in person want to add? Well, in that case, thanks for a really great discussion. I think this has been really illuminating, at least for me. I don't know about everybody else, but it's been great to just kind of understand where the technical roadblocks are and just resource roadblocks are, and the fundamental things that we're going to have to overcome, like data reduction. So thanks.
And thank you, Curtis, for chairing the discussion. So we have one presentation at the end of this session from Destry Saul. Destry, I see you online.
Rachel. Perfect. Yep. You hear me all right?
Yep.
Great.
I will stop sharing our screen.
Great. And I'll share mine.
And share yours.
Let's see. That works. Here. There we go. That.
Okay, we see your screen now.
Seeing some slides. Great.
Take it away.
Awesome. Hi, my name is Destry Saul. Nice to meet everybody. Sorry I can't be there in person. My talk is not radio astronomy, even though that is a little bit of my background. Thank you, Rachel, for giving me a little slot to talk about a new program and resource that I'm putting together with the Discovery Alliance. So it's called Project Dovetail. The blurb here at the top. Project Dovetail provides targeted software engineering support to accelerate science and launch discoveries that otherwise would not be made. What it is it's software consulting at the contracting at its simplest. Like it says here, the engagements include consultation, exploration, and definition, followed by a managed engineering effort. But what is it really? Services, not products. That's a thing I'd really like to stress, which I think is not as common in astronomy and science. We're not building, while we might build things, we don't build things for ourselves. We provide the service to help other people build things. That may be from scratch, or that may be just helping an existing effort. The project brings together 4 different groups of people that I think are pretty important as far as making this sort of thing work in a scientific context. We have the Discovery Alliance, the LSST Discovery Alliance. They are the admin, they're providing admin support. as well as fundraising, as well as finance, moving, blah, 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 that sort of stuff. We have professional software engineers, as you'd expect if we're doing software consulting. We have astronomers turned software engineers. And this is, I think, a special exciting bit about this program. This is where my background is. I should probably introduce myself. Hi, I'm Destry. I got my PhD in 2013, doing radio work, actually. But then promptly went to industry, did 10, 11 years in industry as a software engineer, a data scientist, then more traditional software engineer. And then I ended that with 2 years at NORLab as a staff software engineer. So astronomer, but for the past 10 years have been living software very full-time. And so people like myself are filling this role called that we're calling solution engineering, which is people who can speak both languages, who both talk about astronomy and science, though not practicing scientists, but can also speak to software engineers and provide that translation layer between the two groups. And then, of course, we have astronomers, scientists. I know also this group in particular, we have other developers, full-time astronomy developers. I think you fit sort of halfway between the software engineers and the astronomer category here, where you're subject matter experts. You are professionals, but you also speak science as well. So I guess actually you kind of fall in all three. Again, dear to my heart, I did it for several years. What is not Project Dovetail, I think, is a good thing to answer right away, is we don't do science. Not scientists. We have no scientists on staff. We are engineers and developers. We're here to help, but we're not here to do the science. So what that means in a project is we won't write algorithms, but we can implement them, we can improve them, we can optimize them, those sorts of things. But the background and the sciencey part, we don't do that. And we also don't do long-term operations and support. The point of this program is to bring in part-time or short-term software engineers who otherwise wouldn't be available for full-time employment. If you need a full-time engineer, you should hire a full-time engineer. That's not what we're trying to replace in any way. So these are my theses, the idea behind some of the ideas behind this program is I think there's near infinite work to do. I think from what I've heard so far, people in the room will agree with me there, but it can be irregular and bursty. Sometimes you need particular skill sets for certain amounts of time. Sometimes you need a lot of work, but only for a certain amount of time. And then on the other hand, which I think is less clear to folks, is I think there's near infinite skilled labor available. I think there is a deep well of extremely experienced software engineers who would love to do astronomy work. And so far that's playing out. We've got a good crew already, and we're still just in a bootstrapping phase. I think everyone would benefit from software work. That might be a little over the top, but I think it's pretty much true. Anyone in any place at any stage could use probably a little bit of software for something to speed up your life in some way or make something smoother. Another big one is I think small projects can produce substantial value. I don't need $1 million to build some giant thing. Not that that's not important and people shouldn't do it, but I think for $1,000 that I can contribute substantial value to an existing project or to someone's research, or even less. Honestly, yeah, a couple $100. I think we could probably still do some substantial value for that. I also think that this model that we're implementing is the most cost-effective way to do what I'm proposing. And I think it is still extremely attractive to experienced engineers. It's not asking people to volunteer. It's not asking for people to work for less than they think that they're worth. So here's some examples of, just to give you some ideas, because I think sometimes it gets a bit abstract. Everything with a star is things we're currently either doing or have delivered. It's part of this is to show that we're here to do nuts and bolts stuff. a lot of the time. We can do and look forward to doing lots of exciting, cutting edge, blah 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 stuff, but it doesn't have to be that. And you can get a lot of value out of smaller things. And I'm sure there's folks in the room that some of these probably call out to you. Some of my personal favorites are updating old code. It might sound, again, like a slog to some folks, but I think there's just something beautiful in taking some ancient non-running code and getting it to run fast and in a current environment. What are some of the other highlights here? Ticket burn down. I think that's another one that people forget. Like if you've got a project and you've got tickets and we can just see them, you can just point us at them and we can help you just close out tickets. Debugging, pair programming. The program really is designed to be able to be helpful to anyone. So even folks who can barely code, have helped with just getting code into GitHub or just, getting code to run. Honestly. And this is where things like, a couple of hours can really speed up a project. Another couple down here at the bottom that I'd like to call attention to is cloud database framework stuff. These are things that that folks and the UI, the web UI thing, it's much harder to hack your way through some of that stuff. You gotta take all the time and go and learn all the stuff, all the back stuff, because otherwise you'll just be flopping around, no offense. But if you find a person who already knows everything there is to know about it, it takes them an hour. I'm not a web programmer. And for me, that's one that just every time I have some web work I need to do, if I can just find someone to do it who already knows how to do it, it's such a better use of money. So those are that. Here are some frequently asked questions. I'm going to rush through this. Too good to be true. It's not. We're here. We're real. We're live. Just talk to me. Where do you send your proposals? You don't. We're operating more like a contracting company. So just give me a call. Send me anything, and I will almost hunt you down and ask you how we can help you. That's also a pretty different model that's been kind of hard for some folks to swallow. Why hasn't this existed before? I think this is an important point. The Discovery Alliance in particular is a great place for this program to live, and that they're global. They don't have overheads or the restrictions that some of the academic institutions or national labs have. So they're really an amazing partner. Not partner, I mean, we are the Discovery Alliance. To be able to move incredibly fast. And by fast, I mean very fast. Like we had conversations with people and we start work less than a week later. We don't need to go through a lot of the, the mechanisms that are in place in a lot of the other institutions. There's also a lot more ex-astronomers available than there used to be. So finding these solution architect roles, there's plenty of folks that have had 10, 15 years in industry now and are kind of interested in doing more astronomy again. And then also remote work, we can act globally. The Discovery Alliance on both sides, we can hire globally and we can work globally. So that's pretty excellent. I'm just going to skip the next one. We're specialists, et cetera. Why should you use this instead of hiring a software developer? I think that's an important point again for this crowd. We're not advocating that you shouldn't hire software developers. I just think there are times and places where hiring someone full-time is not the right answer. And also, again, hiring, it can be really hard. So just being able to bring someone in for tens of hours to solve a problem and not having to worry about keeping them long-term and dealing with the process of hiring and blah, blah, blah. That's what we're here to do. And I've honestly heard this so many times now. I don't believe these software engineers exist. Again, just come and talk to me. I will introduce you to them. We will have them work for you. I think our average, I was trying to calculate our average experience across the team, I think is something like 17 or 18 years of full-time experience at as big a companies as you want to talk about. So we're here, we're excited to work. We love astronomy. We want to help, blah, blah, blah. So lastly, if you want to talk to me about it, please just email me or Slack me. You can find me all over the place. I am more than happy to take time and talk to you about details. The one thing that you may be asking, which isn't any of these slides, is what about money? I didn't put that in here on purpose because that could change tomorrow. We are available. You can hire us. Again, I think it's as cost efficient as you're going to find. We're also available right now for Discovery Alliance institutions. We're doing some pro bono small projects. So if you're at one of those institutions, extra reach out to me because I can do work for you for free. Yeah, so that's that. We can talk more about how the finance side works offline. And that's it. Questions?
Thank you very much, Destry. Any questions from the audience?
Hi, this is Griffin Hosenzader from UCSD.
Hey, Griffin.
Hi. About once a week, somebody tells me I should talk to you about Project Dovetail. And
I was just going to say I've been told the same.
Yeah. So, but the thing I still don't understand, that your example slide was very helpful in this. But okay, you want to do, self-contained small projects, and you don't want to do long-term support, right?
Yes.
Where's the boundary there? What kind of scope can you handle, or you're interested in doing? Like, is it some code that already exists and needs to be fixed up, or you want to like write something totally from scratch? And then, there's going to be some long-term component of that maybe I have to do afterwards, right?
Yeah, so that's an important part with the scoping of the projects is who's going to own it after we're done. Right? we don't want to just be making code, throwing it out into the ether and having it decay immediately. So working with folks to find what's the right thing, if you want something and you're not going to be able to support it, then maybe we should help you decide that there's something else to build in some way. I don't have any concrete examples for that, but it doesn't mean that just because you don't have any code, we can't write code for you. So we've already done a couple now that are like, oh, someone has a Python notebook and they want it to turn into a Python package, right? They couldn't have written it on their own, but now that they have it, it runs. It doesn't require, as much upkeep. Eventually, it'll rot. And we're aware of that.
Do you have is there like a list of projects you've worked on in the past that I could see what kind of things I could?
We don't have that public right now. We should probably do something like that. And again, right now we're in this bootstrapping phase. Again, the program was defined right in October of last year, and then the funding landscape changed drastically since then, as everyone's aware. So we've had to pivot a lot because asking folks to fund things has been not as fun for conversations. So most of our stuff has all been at the 10-hour scale. So it's also not necessarily representative of what we can do.
Okay, that's helpful. Anyway, but I'll follow up. Thanks.
Yeah, let's chat for sure.
Oh, a couple more questions. Hang on a sec.
Oh, cool.
Hi, Juno Kohlmeyer, Carnegie Observatories. I had a question. If Project Dovetail, if I should think about it more like Southwestern Research Institute, but for software engineering, or should I think about it more like WeWork, but full of software engineering consultants? Is it actually like affiliated with the LSSD Discovery Alliance, like institutionally, or is it actually like a project within it, or is it a separate kind of organization where there are individual consultants that all have a different fee structure and a different plan?
Right. I don't know what was the Southwest, the first bit. I don't actually know that organization, but it is Project Dovetail is a program within the LSST Discovery Alliance. So everybody, the contractors are working for the Discovery Alliance. The Discovery Alliance is providing the services to the different institutions, projects that are available. So you don't have to deal with coordinating with the individuals. A thing I didn't mention is the engagements are all managed. So we have a very experienced engineering manager who will keep track of and make sure that projects are going as planned. in the initial discussions that we had about how this program should look, one of the bits of feedback we had was folks who had tried to hire contractors before had struggled sometimes because there wasn't enough oversight of the engineers, and so sometimes there were communication problems, and what was actually needed didn't get done, right? And so this isn't just here's an engineer, have fun, right? Like it's very much a describe your problem, we'll work with you to find a solution, and then we will get there to the end, involving as much management as necessary to get there. So it very much depends project to project.
We have to wrap it up there because we are now in our first coffee break, but let's thank Destry again.
Great. Yeah, please email me, contact me. Happy to chat as much as you all want. So.
And thanks to all of our speakers from this first session. We have a half-hour coffee break, and then we have a on-conference session. So start thinking about what you want to do with the hour after the coffee break.